Global warming potential. Global warming potential, or GWP, is a relative measure of how much heat a greenhouse gas traps in the atmosphere. It compares the amount of heat trapped by a certain mass of the gas in question to the amount of heat trapped by a similar mass of carbon dioxide. It's an interesting choice to use mass as their measure, since the number of particles or the number of molecules seems like it would be more relevant. The global warming potential is calculated over a specific time interval, commonly 20, 100, or 500 years. Global warming potential is expressed as a factor of carbon dioxide, whose GWP is standardized to 1. For example, the 20-year global warming potential of methane is 72, which means that if the same mass of methane and carbon dioxide were introduced into the atmosphere, the methane will trap 72 times more heat than the carbon dioxide over the next 20 years. So I'm trying to imagine a methane molecule with its carbon in the middle with about size 12, and its H with 1, 1, 1, 1. It weighs 12, 13, 14, 15, 16 atomic mass units, whatever that's called, while a carbon dioxide with its O over here and its O over here and its carbon in the middle, this carbon is probably carbon 12, while oxygen is somewhere around 16, and 16. So we'll be adding 16 plus 16 plus 12 is about 44 atomic mass units. So you notice that methane, it's about 3 times as big by mass. So if methane has 72 times the global warming potential by mass, it's going to have about 26.2 times the global warming potential by, let's call it the molar global warming potential. Global warming potential depends on the following factors: the absorption of infrared radiation by a given species, the spectral location of its absorbing wavelengths, and the atmospheric lifetime of the species. So according to this, our specific heat that I was talking about in previous videos really doesn't have anything to do with it. It's just the infrared radiation, and the spectral location of its absorbing wavelengths is the same thing. I mean, it's the infrared radiation. They also don't mention reflection of infrared radiation, which maybe when they're talking about a gas, reflection and absorption are effectively the same thing, since if you scatter the light, it's essentially, if the gas scatters the light, it's essentially absorbed, unless it forms a surface, in which case scattering the light, or if the light is scattered from the top, then it'll reflect right off of it. But if it's scattered from the bottom, then that's essentially absorbed. So, where was I? A global warming potential correlates with a large infrared absorption and a long atmospheric lifetime. I feel like they're leaving out things like heat conductivity and specific heat capacity. And I feel like we shouldn't just be talking about the spectroscopic absorption rates. There's something else. The thermal absorption. I'm wanting to have a look at this Aura space satellite. I'm not sure where I'm going with this, but it sure is pretty. Okay, well, actually it looks more like a big yellow box. But does it take pretty pictures? Well, it sounds like good news. NASA satellites confirm sharp decline in pollution from U.S. coal power plants. The ozone monitoring instruments on NASA's Aura satellites to confirm major reductions in the levels of key air pollutants generated by coal power plants. Here's the global nitrogen dioxide from the scene from the Aura satellite. It actually spins around there and you can see it. Wow, it's just going crazy, isn't it? Let's see the other side of the planet. Here's some stuff over in China. and the south side of Australia and the northwest side of Australia. That was pretty interesting. Of course, comments are disabled for this video. Now we're getting into the, oops, get over here with Europe and Asia all exposed. Here's an ozone hole floating around over Antarctica. Don't know for sure what to say about that. That'd be where the magnetic field is popping out of the Earth. I do know that much. But it seems to be getting bigger, smaller, floating around, moving around. I'll tell you what I was looking for. Aura has done some video or pictures of some cosmic gas type, interstellar gas. And the interstellar gas, I wanted to get an idea of what they were saying as the interstellar gas, like what kind of radiation it's putting out, what temperature it's sending stuff out at, whether that's thermal radiation or if it's spectroscopic radiation. Anyway, I went out to this Aura astronomy, and it looks like this is not related to the Aura Space Telescope. But if I look up the Aura Space Telescope, I get some definite pictures in here of some things that are far away. But unfortunately, the reason for that is that Google thinks I was looking for just Space Telescope, and it just ignored the word Aura. There's good jobs at the Aura Space Telescope Science Institute salary. So let's come back to this global warming potential article. A high global warming potential correlates with a large infrared absorption. Oh, I already read that. The dependence of global warming potential on the wavelength of absorption is more complicated. Even if a gas absorbs radiation efficiently at a certain wavelength, this may not affect its global warming potential much if the atmosphere already absorbs most radiation at that wavelength. A gas has the most effect if it absorbs in a window of wavelengths where the atmosphere is fairly transparent. Because global warming potential of a greenhouse gas depends directly on its infrared spectrum, the use of infrared spectroscopy to study greenhouse gases is essentially important to the efforts to understand the impact of human activities on global climate change. The radiative forcing capacity, being the amount of energy, for instance joules, per unit area, say per meter squared, per unit time, per second, that is watts per meter squared, which is the same unit as intensity. And that is what is absorbed by the greenhouse gas that would have otherwise been lost to space. It is expressed by the formula the sum as n goes from 1 to 100 AB S sub I times F sub I divided by path length times density. Alright, there seems to be a flaw in this formula because they've got an n over here and an I over here. Usually if there's a subscript over here, it ought to match this letter here. Subscript I represents an interval of 10 inverse centimeters. Unfortunately, that doesn't really have much meaning to me. Ab sub I represents the integrated infrared absorbance. So ABS stands for absorbance. And F sub I represents the RF for that interval. So that would be the radiative forcing for that interval. So for instance, with that equation, with the description of these variables here, I'm not entirely sure that I would be able to figure out what that equation meant. And they also say verification needed, like a source for that equation. Path length, I can speculate what that might mean. It's perhaps the distance that a particle will go before it runs into another particle, maybe a mean path length. Density would be probably, well, the density of what? That would be an important question to answer. The density of the atmosphere, or is it the density of that particular greenhouse gas. ABS is the infrared absorbance of the sample in that interval. So 1 to 100, it's going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 100 inverse centimeters would be what? This would be a sum going from 1 per centimeter, 2 per centimeter, 3 per centimeter, 4 per centimeter, all the way to 100 per centimeter. Except for the fact that this is an I, and they're not incrementing I. So, but I bet they meant to increment I. So what's next? The Intergovernmental Panel on Climate Change provides the generally accepted values for global warming potential, which changed slightly between 1996 and 2001. An exact definition can be found in the IPC Intergovernmental Panel on Climate Change's 2001 Third Assessment Report. GW is defined as the ratio of the time integrated radiative forcing from the instantaneous release of 1 kilogram of a trace substance relative to that of 1 kilogram of a reference gas, where TH is the time horizon over which the calculation is considered. A sub x is the radiative efficiency due to unit increase in the atmospheric abundance of the substance, i.e. watts per meter squared per kilogram. So this is the amount of radiative efficiency it increases per kilogram. Now, what does radiative efficiency mean? Does that mean its ability to absorb heat, or its ability to capture heat? Probably its ability to capture heat per kilogram. So is this going to be a tiny amount? Because, I mean, this is a kilogram that you're adding to the entire world, and this is the effect that it has over a single square meter, probably. Let's see, x of t is the time-dependent decay in abundance of the substance following an instantaneous release of it at time t equals 0. So what does that mean? X of t is a factor, something like maybe e to the negative kt or something like that. That would make an exponentially decreasing thing. Or with a half-life, it could be 1/2 to the t over its half-life. That's usually, I like that method of writing exponential decay. This way is handy if you're doing some calculus, but which of course we are doing some calculus here, aren't we? So since we're integrating, it'll probably be easier to have it in this form. So here we go. This is linear, or we're assuming that the radiative efficiency is a constant, completely proportional to the atmospheric abundance of the substance in the atmosphere. So this would be a good question. This does clearly have an assumption of linearity here. It's not going to be, well, quite frankly, with these tiny additions of 1 kilogram of the gas at a time, of course, that is going to be linear, because in general, if your order of magnitude of the additional gas that you're adding to the entire system, an atmosphere the size of the Earth, and you add 1 kilogram to the mass of the substance, then we can probably assume that over a small region, at least, that would be a linear effect. But it does look like they go ahead and bring up nonlinear behavior down below. Right there, it says a few important greenhouse gases display nonlinear behavior for current and likely future abundances. For instance, carbon dioxide, methane, and N2O. For those gases, the relative radiative forcings will depend upon abundance and hence upon the future scenario adopted. In other words, A sub x is not going to be a function. It's not going to be a constant. It's going to be a function of x of t. So you have A of x times x of t. Integral of A of x of t times x of t, right? tt. No big deal. Since all GWP calculations are a comparison to carbon dioxide, which is nonlinear, and this is something I was asking about earlier, all GWP values are affected. So why would you do it that way? Why would you make the comparison to carbon dioxide? Why don't you use simple watts or watts per meter squared or something like that? I'm sorry. It just seems like you'll end up with some extremely misleading numbers if you are consistently always comparing your global warming potential to a carbon dioxide gas down here, which we're already confused about the carbon dioxide gas, aren't we? Well, let's put it this way. If we are looking for the global warming potential of carbon dioxide gas, by this definition, the global warming of carbon dioxide gas is going to always be equal to exactly 1, which is kind of not a particularly useful unit of measurement, but I am probably misunderstanding something that cooler heads are already doing correctly. Well, people that have been working on this for years rather than me, who am just looking at it for the first time today. But yeah, there it is. Carbon dioxide has a global warming potential of exactly 1. So let's say, for instance, what if carbon dioxide's global warming potential is, like, if you get over a certain temperature, it's basically nothing, and then you're dividing by nothing. Something divided by nothing would be, say, 16,300 or 12,000 or something, some big scary number like that. And it appears that they assign a little bit more complexity to the thing. Methane has a potential of 25 over 100 years, but 72 over 20 years, because the GWP value depends on how the gas concentration decays over time in the atmosphere. So you need to make a point of indicating your time horizon, the 20-year global warming potential versus the 100-year global warming potential, because a gas that stays for a long time and has a very low decay rate is going to last for longer. So in essence, if you have the functions, in essence, what you really need here is, number one, screw the denominator, because we're going to be putting a carbon dioxide, an arbitrary carbon dioxide number down there. We need this x of t, which tells us the abundance of the thing, and we need this a of x, which tells us the nonlinear radiative efficiency, and that radiative efficiency is going to be going to also be a function of all of the other gases that are present, because if it's the only gas present that is absorbing radiation in a certain range, then it's going to have a lot more effect than if it is one of many gases that absorbs radiation in that range. But I don't see any benefit to putting carbon dioxide in the denominator here. I can't fathom the use of that at all, because this is going to give you a nice thing that tells you just how many watts of energy the thing is going to absorb. by dividing it by the carbon dioxide